Okay, the next topic we're going to look at is amino acid synthesis. This can be used to make natural amino acids or even unnatural amino acids, which is under a lot of investigation now. There's a lot of cool research being done with kind of custom polypeptides that include non-natural amino acids. And the first way we can do this is using the Hell-Volhard-Zielinski reaction. And this is a reaction that we actually covered during our carboxylic acid chemistry chapter. And if you remember, this reaction involved alpha carbon chemistry of a carboxylic acid. And the alpha carbon, like we said, is going to be that carbon right next door to that carboxylic acid. And in step 1 of this reaction, we react it with phosphorus tribromide. That converts this OH group into a Br group, thereby making it an acid halide. And we react it with elemental bromine. That brominates the alpha position. But then in step 2, to get the bromine off of this position, I know it's not shown now, we want to quench this entire reaction with water. And that will convert it back to the carboxylic acid. So really the net impact of this reaction is you get a bromine installed directly on that alpha carbon, right? So this is our alpha position. However, there's a big pitfall to this, and that is we've created a new stereocenter here, and we can't control whether or not the stereocenter is R or S. And like we said, in nature, most amino acids are going to be L amino acids. So this creates kind of a problem. We would have to purify out the correct enantiomer, isolate it, and then carry it forward. But that can be done. So I did want to make a note that this is going to be a racemic mix. And then what we can do next is we can treat this with ammonia in excess. And that will essentially just do SN2 chemistry with the bromine, right? However, ammonia is also a base. And because it's a base, if we use it in excess, it's also going to deprotonate the carboxylic acid. So at the end, what we need to do is consider this, that we would swap out the bromine for an NH2 group, but in order to convert this back to an OH group, we need to treat it with strong acid. So we react this with H3O+, which in the end would actually protonate the NH2 group into an NH3 group. So the net product for this reaction would be your ammonium salt. And again, we still would have that racemic mixture. And then what you can do is adjust your pH to get to your correct isomer, or sorry, your correct charge species. So you can adjust pH, and then you can purify. All right, so it's not really the most elegant method. You're going to lose at very minimum 50% of your starting carboxylic acid due to the racemic mixture, but it works. It's kind of old school, but it works. All right, the next one is also fairly old school, and it's another familiar one. This is the Malonic Ester variant. And this is another reaction that we saw in the alpha carbon chemistry chapter. And if you remember, in that chapter, we had this starting material that was diethyl malonate. However, this time we're going to use a slightly different starting material, and it's going to have this group coming off of it, this N-acyl group. And the neat thing with this is you can buy this commercially. It's nice and cheap. It's commonly bought at a lot of these chemical companies. And same thing here. We've got this alpha position in between both carbonyls, and that means that this proton coming off right there is going to be relatively acidic. So it's pretty easy to deprotonate. And like I said in this chapter, if we want to deprotonate this, we also want to make sure that the base we use corresponds to the leaving group on our ester. That avoids any unwanted transesterification. So what I would do is use NaOET. That way this ethoxy group matches the ethoxy group on my ester. We don't get any unwanted side chemistry. That would allow us to deprotonate that alpha proton. And then we can do SN2 chemistry. So we can treat this with some sort of alkyl halide. And the key thing here is we want this to be the R group for the amino acid. This is somewhat limited though, right? Because we need to make sure it's unhindered enough to do SN2 chemistry. So we can't make all amino acids this way, but we can make some of them. And when we do this, we would get a product that looks a little bit like this. We would have that N-acyl group still hanging on, but now we would have the R group installed on that alpha carbon as well. All right, next step is we want to treat this with acid and heat. And this is kind of neat. Like I said, the first thing that you're going to do is you're going to convert each of these esters to carboxylic acids, right? But then when you convert that to a carboxylic acid, one of them can be blown off as CO2. So let's make some notes here. So for example, one side will get converted to a carboxylic acid. This entire side could get lost as CO2. Some students will ask me, does it matter which side? No, not at all. The other side could be lost as CO2 and the opposite side could be the carboxylic acid. Doesn't matter. However, it is important to remember that one of them will be lost as CO2. The other one will be lost as carboxylic acid. All right, the other interesting thing is if we think about down here, we've got an amide bond, right? And amides can also be cleaved using acid and heat. So what's going to happen is this is going to be hydrolyzed. And we're going to lose that acyl group. Sorry, let me clean this up a little bit. And let's take a look at the final product that we would get out. So in the end, we're still going to be left with our carboxylic acid. We're still going to have this R group. And then the nitrogen here is going to be completely protonated to the ammonium state. And just like before, we're going to run into this problem where it's racemic, meaning we're going to get both R and S stereochemistry, but just like before, we can adjust the pH and purify it. As you can see, it's definitely not a reaction with good atom economy or good yield, right? We're going to lose a lot of our yield due to this racemic mixture, and the atom economy is going to be pretty poor. We're throwing in a lot more atoms as starting material than we're getting out in our final product, but it works. All right, there's one new one I did want to go over, and this is called the Strecker synthesis. All right, and in this reaction, you first start with an aldehyde. And what you do first is you treat this with ammonium chloride, that's NH4Cl, and sodium cyanide. It's kind of weird to think about, but ammonium chloride, if we look at it, is really just a weak acid. Okay, so if we put ammonium chloride in there, it could protonate that aldehyde, or at least a little bit in equilibrium. I'm not going to bother with drawing equilibrium arrows, but you get the idea. Some of this will be protonated, and then when we do that, we're going to have a small amount of ammonia around, right? That would be the conjugate base of the NH4 from the ammonium chloride acid. And then in the next step, this could attack in and kick up electrons. It's a great nucleophile. All right, at this point, we're going to have an OH group coming off, and then we're going to have an NH3 group coming off, which means that nitrogen will have a positive charge. And as you're probably used to at this point, we're going to do a proton transfer. And what this means is we're going to take one of these protons from this nitrogen and move it over to the alcohol and turn that alcohol into a good leaving group. So now it's going to be OH2 and NH2, and the oxygen will have a positive charge. And like I said, this is a really good leaving group. So like we've seen many times before, we can clamp down, kick off our leaving group, and we can form our aminium ion. And water would be kicked off as our leaving group. All right, so this is our aminium ion. An aminium ion is just an imine that's been protonated, right? And we've kind of been neglecting the cyanide up here. So let's take a look at what happens when cyanide encounters this aminium ion. Well, cyanide has carbon with a negative charge, which means it's a pretty good nucleophile. In fact, we can even show this as a carbon-nitrogen triple bond just to be thorough. And this can attack into our aminium ion and kick electrons all the way up to that nitrogen. And when we do this, we're going to form a tetrahedral intermediate. Let me actually just clean this up as NH2. And we've got our tetrahedral intermediate. All right, in our last step, what we're going to do is we're going to treat this with strong acid and heat. And I'm not going to show this full mechanism because it gets pretty lengthy, but as you saw in your problem of the day a while ago, we can convert this nitrile into a carboxylic acid by reacting it with acid and heat. So that whole group's going to get converted. Into a carboxylic acid group. And then the NH2 group, if we're under acidic conditions, is going to be protonated into an NH3 group, and we've got our final product. This is our amino acid, right? We've got our carboxylic acid, we've got our amine, and we've got the appropriate R group. So it is important to remember that the aldehyde that you start with, the R group should be the R group you want in your final amino acid. But just like in the previous two examples, what we've done is we've created a racemic mixture. And because it's racemic, we would first have to adjust the pH and purify. However, you could do this to make a custom amino acid. All right, the last one is arguably the most popular one now, and this is the Enantio selective synthesis. And as you can tell by the name, Enantio selective means that we're only going to get one enantiomer. We're not going to get this racemic mixture that's causing all these problems. All right, and the starting material for this is a bit more complicated, but again, it's commercially available, and it still has an acyl group coming off of it. And what we do first is we treat this with hydrogen gas, so H2 gas, and then we need a chiral catalyst. And because it's a chiral catalyst, it's only going to deliver hydrogens to one face of this alkene, meaning the hydrogens are going to be cis, but are they going to add top or bottom or both? A chiral catalyst ensures that they're only delivered to one face. All right, so we're going to reduce that double bond in step 1. Then in step 2, what we're going to do is we're going to hydrolyze off this amide group, kind of like we did in the previous problem. And this is done in 2 different steps. They do NaOH and H2O. However, in order to ensure that everything's protonated in the end, they treat it with strong acid. All right, so in the end, you get your R group over here. And the neat thing with this, kind of like I was saying before, is both hydrogens are going to be added to the same face. So we would have hydrogen here as a dash and a hydrogen there as a dash. So we're able to ensure that we get a product that is enantio pure. So we don't get a racemic mixture anymore. So now the question is, what in the heck is a chiral catalyst? If you go on and take more chemistry, specifically organometallic chemistry, you'll cover this in a lot more detail. But one of the common catalysts is called R plus ruthenium binap dichloride. All right, so let's take a look at what this looks like. The binap group is short for binaphthyl, and naphthyl are two fused aromatic rings. And this would be naphthyl, but because it's binaphthyl, we have to have two of them. That look like this. All right, so we've got two naphthyl groups fused together. The cool thing with this is because there's hydrogens here and here, they can't actually lay flat. And so instead what we're going to do is we're going to twist them slightly so those two hydrogens don't run into one another. And when this happens, you develop something called axial chirality. So it's not true chirality like we're used to. Instead, it's something that's chiral without having a true chiral center within it. It's kind of an odd example. And then off of each of these ends, we've got phosphorus atoms. And each of these two phosphorus atoms have two phenyl groups. And then each of those phosphorus atoms is coordinated to a ruthenium atom, which are quite expensive. And the ruthenium has two chlorines off of it. But this binap group helps transfer its chirality to the final product. So this is called a chiral ligand. And it helps transfer chirality to the product and ensures that we only get one enantiomer. It is fairly complicated, but I just wanted to show you in case you go on and take any more chemistry after this. All right, in our next video, what we'll do is we'll look at peptide synthesis, both at a benchtop setting and then in an automated setting.